Good morning, everyone. First of all, I'm very honored to be here. And I would like to give my thanks to all of the organizers and everyone involved. My name is Cor Steging. I'm a PhD student from the University of Groningen from the Netherlands. And as part of the National Hybrid Intelligence Center, our aim is to combine human and machine intelligence. So to expand human intellect rather than to replace it. And one of the challenges that we face is explainability. And though I personally am by no means an expert in the field of law, because my background is in AI and I worked as a machine learning engineer in industry, but what I do know is that explainability is also one of the most crucial aspects in AI systems, in AI and law. Because if a system cannot be explained, it cannot be justified. And systems that cannot explain their decision making, therefore, seemingly have no place in AI and law. Current state of the art machine learning systems, on the other hand, like deep learning, are exactly examples of such systems that cannot explain their decision making. They are black box systems. And this is unfortunate because their performance in terms of making autonomous decisions is, of course, outstanding and beats standard knowledge driven methods. And this conflict between, on the one hand, a high performance and on the other hand, a lack of transparency has now led to the well known field of explainable AI. And using explainable AI techniques, the decision making process of such black box systems can be explained. And even though these methods are still far from perfect, they are making some substantial steps forward. But for us, however, this is where the problem starts. This is because explainable AI techniques have highlighted an interesting phenomenon. For example, using the line method, a wolf versus husky classifier is explained. And this classifier performed well in terms of accuracy. But when we take a look at the reasoning behind its decision making, we see something interesting. This husky here is classified as a wolf because there is snow in the background, a seemingly irrelevant detail. It should at least be irrelevant in the classification process. And this strange phenomenon arises even with high classification accuracies and has been shown time and time again. Think, for example, of adversarial attacks, wherein just a slight perturbation of an image can lead to drastically different predictions. And we refer to this phenomenon as systems that perform well, but for the wrong reasons. Explainability alone is therefore insufficient in our goals of AI and law. Explaining unsound decisions does not make it sound. Instead, we want something more. We want systems that perform well for the right reasons. What we want is we want responsible systems. And we are now working towards a method that can act as a first step into reaching that goal, a method to evaluate the decision making of a system, or in other words, a method for rationale evaluation. And here we define the rationale of a system as the reasoning that that system uses to come to its decisions. The method that we propose is model agnostic and should therefore work with any machine learning system because it's more of a generalized concept that is driven by knowledge from domain experts in order to evaluate the learned rationale of a system. We believe that by aligning learning and reasoning, we can potentially achieve a best of both worlds situation. And our method is very loosely based on the idea of unit testing in software, in professional software development, wherein you write tests for each of the smaller components or functions of your code. Now, the method that we propose consists of three distinct steps. First of all, we measure the accuracy of a trained system, and we proceed only if the accuracy is sufficiently high. Of course, sufficiently high in this sense is subjective and is based on the specific problem at hand. But the point of this first step is that if the accuracy is not sufficiently high, then the rationale will not be sound either. So there's no point in evaluating it. Now, in step 2, we design dedicated test sets for rationale evaluation, targeting selected rationale elements based on expert knowledge of the domain. And these test sets are designed such that systems can only perform well on these test sets if it has learned the specifically targeted element of the domain. And lastly, we evaluate the rationale through the performance of the trained systems on these dedicated test sets. And furthermore, based on this evaluation, so based on this entire method, the training data can then be adjusted to improve the rationale, again, based on knowledge of the domain. We performed a couple of experiments in which we illustrated our method, and in each experiment, we aimed to use our method to evaluate the rationale of a system, so the reasoning behind its decision making. All of the data that we use is artificially generated, based on knowledge structures of fictional and non-fictional legal domains. And each domain can be defined explicitly as a set of conditions. And this was intentional, as this makes it possible to compare these conditions to the rationale of the system. In other words, we have an objective ground truth to compare to. And though they are simple toy domains, they were chosen to introduce and to illustrate our method in an objective manner. We first replicated a study done by Ben Schapen in 1993, as this study inspired us, and it illustrates the current issues regarding responsible AI in a very intuitive manner. It investigated the soundness of the rationale of neural networks through the use of artificially generated data. And this data was based on a fictional domain in which pensioners were eligible for a welfare benefit if and only if they satisfied 6 conditions. And these 6 conditions are expressed logically here on the right of the slide. If and only if all of these 6 conditions evaluate to true, the label, eligibility, also evaluates to true. What we did is we replicated this study using more data with standard state-of-the-art multi-layered perceptrons. We even introduced a simplified version of the domain and did all of this to see whether the claims that were made back then still hold today. And they do. When we train and test a neural network on these data sets, they initially attain very high accuracy scores of around 99% on this fictional welfare benefit domain. So step 1 of our method, which is checking whether the accuracy is sufficiently high, is therefore completed. According to the second step of our method, we generate 2 dedicated test sets, which are designed specifically to measure how well these 6 conditions are learned, or at least 2 of these 6 conditions. By testing trained networks on these data sets, which is step 3 of our method, we discovered that the system was unable to learn both of these conditions. Systems can therefore attain high accuracies while only really knowing 4 out of the 6 conditions that define the domain. And even with modern MLPs, multi-layer perceptrons, with more data and by simplifying the domain, the same results still stand. We have high accuracies while not knowing all of the conditions that define the data. Or in other words, we have an unsound rationale. By adjusting the training data based on this evaluation, the initial accuracies remain almost the same, but the individual conditions are learned significantly better. An example of this can be seen in these graphs. These display just 1 out of the 6 conditions that a system had to learn. So first on the left, we see an ideal graph, what we would like to expect. And in the middle, we see the actual graph. What we can conclude is that the system was not able to approximate the condition. After adjusting the training set based on our evaluation, the graph on the right, the results look a lot better. After replicating the study using the fictional welfare benefit domain, we set out to employ our method in the non-fictional domain of Dutch tort law. And unlike in some countries, Dutch tort law is a statutory law and not a case law. And it describes whether or not there are duties to repair someone's damages given a set of facts, which can be represented as an argumentation diagram as shown here on the right. We can represent this diagram as a set of conditions as well, just as before, as shown here on the bottom of the slide. And again, if and only if all of the conditions evaluate to true, the label evaluates to true. In other words, in that case, there's a duty to repair damages. The network should therefore learn all of the 5 conditions. Again, we generate all kinds of data sets using this domain, and we train neural networks on the data set. Of course, our goal is to investigate how well the conditions are learned. And in particular, we wish to investigate whether the systems are able to learn the notions of unlawfulness and imputability. And just as in the replication study, and according to step 2 of our method, we therefore generate a dedicated test set for both of these conditions, on which a trained system could only perform well if it has learned said condition. What we discovered is the following. First of all, we get high accuracies on a normal test set of above 98%. It is therefore possible to approximate Dutch tort law with a subset of the cases. And step 1 of our method, to measure whether the accuracy is sufficiently high, is therefore complete. When we investigate the performance of the same networks on the dedicated test set, step 3 of our method, we see that despite high accuracies on the regular classification task, one of the 5 conditions, imputability, was hardly learned at all. So to conclude, we have reaffirmed that a high performance does not guarantee a sound rationale. accuracies alone are therefore insufficient. We need something more. So secondly, we also introduce a knowledge-driven, model-agnostic method for rationale evaluation. And in future research, we would like to expand upon this method, such that the soundness of the rationale can become more tangible and that its quality can be asserted. We should again here note that both the machine learning algorithms and the domains that we use in these experiments are toy scenarios to illustrate our methods. We chose MLPs because they are simple black box systems, but our method is generalizable to the most advanced deep learning systems since it is completely model agnostic. We also explicitly chose to use artificial data based on a set of conditions, as these conditions act as our ground truth, thus making it possible to objectively evaluate the rationale of the system. In the future, we might expand to real-life datasets where the ground truth is not as explicit. And in those cases, our method would still rely on the domain knowledge of experts, because in cooperation with these domain experts, we can create dedicated test sets that evaluate specific components of a desired rationale. And we can then compare that to the actual rationale. And this hybrid approach of combining knowledge with reasoning can hopefully move us towards an AI that is not only explainable, but truly responsible. So thank you all very much for your attention. I would be honored to answer any of your questions.
Thank you very much, Mr. Steging, for your brilliant presentation. Now we have a special question from the audience. First, a comment. Mr. Trevor Bench Capon is here with us. He's saying that it's a very nice work, and he has a question. He says, where is the evidence that ML-based systems are more accurate? Generally report success around 80% against 90% for traditional methods. They are quick, but not more accurate.
Right. Thank you very much, Trevor, for that brilliant question. It's a very good one because, of course, that was a generalized statement that doesn't hold in every situation. Of course, when we expand our view beyond just law, we see that in things like computer vision, speech recognition, all these other kinds of domains, machine learning works significantly better than standard good old-fashioned AI. And therefore, our philosophy is that we shouldn't completely abandon machine learning because it is not explainable or works just as well as good old-fashioned explainable AI techniques. So therefore, we wish to investigate these very deep and at the moment state-of-the-art systems so that we can use this as well. But thank you for your question.
Thank you, Mr. Stegin. Now you have 1 minute for final words.
All right. So I would again like to thank everyone involved in the IKIL, so the organizers, the speakers, and of course also the audience for listening. Furthermore, I would like to give my thanks to the co-authors of this paper, to Bart and Celia, also to the Hybrid Intelligence Center for making this work possible, and of course a special thanks to Trevor Bench-Capon for inspiring us. We aim to continue our work on this method of rationale evaluation such that we can move forward towards AI that is both explainable and responsible. Thank you very much.